So in an older video, I showed you how to integrate x squared times e to the x dx, which using integration by parts, you can get it. I want to show you a table method, which will certainly speed up the process. But first, let's just go through again how we do this. When we use the Liate principle, I see this is algebraic first, and then I see exponential here. So e to the x. So a comes before e, so I'm going to pick u to be my algebraic x squared. Then that means that du is 2x dx. And then dv, which is my exponential, is e to the x dx, and my v is e to the x. Okay? So once again, we walk through, I'm just going through this quickly. This was in a previous video, but just rehashing it. Now, I take integral, it's uv, which is x squared, e to the x, minus integral v du, which is 2x dx, right? Okay. And so, once again, I'm going to take this 2 out here because it's a constant. And I need to do a u substitution again here. U equals x, du equals dx, dv is equal to e to the x dx, and then v is equal to e to the x. And so what does this become? Well, it becomes x squared e to the x minus 2, and then all of this, without the negative 2 there, gets replaced with my integration by parts substitution, which says what? uv ex e to the x minus integral v du is substituted in here. And so what does it become? It becomes x squared e to the x minus 2x e to the x. And then minus and minus becomes a plus 2 e to the x, which integral e to the x e to the x, and then plus c. Okay? So that was a very sped up version of integration by parts. I had to use integration by parts 2 times here to get my final answer. I want to show you the table method on how to do this even faster. Okay? So with any good T-table method, I'm going to create a table where on the left I have my u's where I take the derivative. And on the right, I have my dv's where I integrate. Okay? So what did I pick for u? I picked x squared to be it. Okay? So I'm going to put my x squared here. And then what was my dv? My dv was e to the x. All right? So now what I'm going to do is I'm just going to start taking derivatives like a madman. So if I do that, derivative of x squared is 2x, derivative of 2x is 2, derivative of 2 is 0. I can stop taking derivatives after 0, it doesn't count anymore. Okay, so this is the table method. So you might be saying, well, what's going on, Mr. Clark? What are you doing from here? Well, now I want to integrate. Integrating e to the x is easy. It's e to the x. Integral of e to the x again is e to the x. Integral of e to the x. If I keep integrating a million cajillion times, it's always going to be e to the x. It never goes away. Okay, pretty awesome. All right. Now, the trick here, which if you could call it a trick for the table method, is the last part we got to do is we got to add in our plus and minuses. Okay, so what do I mean? The first row is a plus, the next row is a minus, the next row is a plus, the next row is a minus, and it just alternates as far down as you go, okay? So how does this work? All right, so the way this technique works, okay, so remember we're integrating x squared e to the x dx, right? The way this technique works is I multiply on the diagonals, okay, and I integrate across the rows, okay? So I'm going to multiply on the diagonals until I get down to a point where I can integrate, simply. So if I do this, if I multiply down this diagonal, what is this diagonal here? Well, that is x squared e to the x. Okay? If I multiply down this diagonal here, what do I get? I get minus 2x e to the x. Oh my goodness, y'all. Y'all see what's happening here? This is matching perfectly. Okay? And then this next one is plus 2 e to the x. Woohoo, right? And then the last one, well, we don't have a diagonal, but 0 times, if we did go another one, that would be 0 times e to the x, which would just be integrating 0, okay? But if I integrate 0, I mean, that doesn't really do anything, right? So 0 times e to the x, that's just plus 0, right? So really, once we get to that point, there's nothing left to do but add that plus c, okay? Now, but I want you to note, I said something a little weird. I said that we took integrals on the horizontal. So what does that mean? Like that last row there, if I integrated, instead of just writing my plus c here, say I integrated, so it's minus the integral of 0 times e to the x dx. Well, 0 times e to the x, that's just 0. Okay, can we agree 0 times something is just 0? Well, the integral of 0 is the constant c, so that's where that plus c comes into play. So the question might be, well, what if I had not gone all the way down here, but maybe I stopped a little earlier than I should have? Maybe I didn't do this last part here, right? So maybe I just did to here, okay? And then I decided, well, I want to now integrate across the row. So remember, you integrate across the row. And so what does this become? It becomes integral of plus 2 e to the x dx, right? Okay, so what is that equal to? Well, we know what that integral is. So once again, this is going to transfer down. Okay, this 2 can come out front. The integral of e to the x is e to the x plus c, and that's my answer. It's still the same thing here. So this is what I mean by you integrate across the rows and you multiply on the diagonals. So if you want to skip, you see we did this problem 2 different ways here. I was just showing you what would happen if you integrated across the row instead of multiplying. Even multiplying across the diagonal or integrating across the row still got me that same answer that I wanted, okay? So let's do another one from start to finish, and hopefully this will be even more clear for you, and you'll start to see the power of how quickly you can work through these. So x to the 4th e to the 3x dx, okay? So let's work through this. Now, when I use the table method, so I might say on an exam, use the table method to solve this one. This is what I'm talking about, using this table method, okay? If I just say use integration by parts, don't use the table method, then use what we've done in previous videos where we work through it kind of like we did through here, right? Okay. So let's use the table method here. So I got my u and I got my dv. So once again, algebraic comes first, then exponential. So I'm going to use x to the 4th here because I can just take derivatives of this real easily. And if I start taking derivatives, I'm going to work my way down. 24x here, 24, and 0. Okay, so that would be a lot. That would be like 4 iterations of integration by parts to get through this if you did it the long way. Yuck, right? Integrating e to the 3x. Well, the derivative of e to the 3x is 3e to the 3x. So the integral would be 1 over 3. Okay? So that's 1 over 3 e to the 3x. And then we pick up another factor of 1 over 3. So 1 over 3 times 1 over 3 is 1 over 9 e to the 3x. pick up another factor. Remember, I'm just multiplying by that constant, right? That's where the 1, and then the next one is 1 over 3 times 1 over 3 times 1 over 3. That's 1 over 27 e to the 3x. And then the last one here, well, I guess we might ought to go another one. 1 over 243 e to the 3x. So those are just powers of 3 going down this way. Okay, so it starts to get pretty big pretty fast. So now let's use our rule. Okay, what do? We have plus, minus, plus, minus, plus, minus. That would be where students forget to throw in there, and that's how they would mess up. So remember, I multiply on diagonal, and I integrate across the row. Okay, so integrate across the row. So multiplying on the diagonal, what are my diagonals? Here, 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 and here, right? Oh my goodness. So what does this become? This becomes x to the 4th times 1/3 e to the 3x minus 4x cubed times 1 over 9 e to the 3x plus 12x squared times 1 over 27 e to the 3x minus 24x 1 over 81 e to the 3x, and then plus 24 over 243 e to the 3x. And then the last one here, remember that 0 there, if I multiply through there, I don't even care what that is because 0 times that is 0. And if I integrate 0, I get that plus c. So that's kind of how I handle it. This works for all of them except for the repeaters. In the repeaters, when you get to this point and you see something that integrates across and it's the same as the integrand that you started with, then that's where you flip it on back, okay? So, but this one here, just, to make it as simple as possible, that's what's going on there, okay? So not too much, but still still a lot happening. Technically you could simplify this. 8 and 3 make 24, so a factor of 3 comes out, so that would be like 8 over 81 there. I don't think anything else really simplifies for us unless you want to put the numbers together in the fractions, okay? So interesting technique there. The table method is very powerful. Let's do one where we do have a repeater so you can see exactly what to do there. So let's go to our repeater example of sine x e to the x dx, okay? And so you can do it however you want. It doesn't matter which one you pick to be your u, because neither one of those are going away. They're repeaters, okay? So if that's the case, I'm just going to pick u to be sine because I feel like sine is easier for me to take derivative of, and e to the x is simple either way. So integrals of e to the x are e to the x, so I can just write e to the x as many times as I want. But then sine x turns to cosine x, turns to negative sine x, turns to negative cosine x, turns to sine x, right? And then it just keeps going forever and ever. It just repeats, cycles through, okay? So a lot of stuff going on there. Now, what do we have? Our trick says plus, minus, plus, minus, plus, minus. Those things matter, okay? If you don't put that in, then you're going to mess up the table method. That's one of the tricks to the table method. So we multiply across the diagonals. multiply across the diagonals, multiply across the diagonals, multiply across the diagonals. But if we keep doing that, we would keep going forever and ever and ever. So we got to come to a situation where we see that same integrand again or some constant multiple of it. Otherwise, we can't use that trick where we flip it over to the other side like we did in the repeaters video. Okay? Remember what I said. I multiply on the diagonal, but I integrate across the horizontal. So where do I see that sine x e to the x repeat again? Well, it's obviously it's at the first, right? But it's not here, but it is here. Why is it here? That negative here is just differing by a constant multiple there. Okay, so what we're going to do is we're going to multiply across the diagonal and then multiply across the diagonal. And then this last step, we're going to multiply across the horizontal. So what does this get me? The first diagonal gets me plus sine x e to the x. And then minus cosine x e to the x. And then I integrate across the horizontal. So I'm integrating negative sine of x. I'm going to pull the negative out. E to the x dx. Okay? Now, why is this crucial that I stop here? Well, what do I notice? This integrand matches this integrand. Okay? So what does that mean? If I add these on both sides, if I add those on both sides, what is going to happen? I'm going to get 2 integral sine x times e to the x dx equals sine x times e to the x minus cosine x times e to the x. Okay? And then how do I solve for this right here? Well, I'm going to divide both sides by 2 and then add my plus c. So my answer is sine x e to the x dx equals what? So if I wanted to get super fancy, I could factor an e to the x out of both of these, which would be e to the x over 2. And then I would have what? Sine x minus cosine x. Super fancy, right? And then all plus c. Don't forget that plus c there. That'll bite you. Okay, don't let it bite you. All right. So that is an instance where you can use the table in order to solve a repeater. Remember, with a repeater, you got to integrate across the row, all right, to find that integral that matches with what you started with, okay? If you have a problem where it's algebraic, you can just take derivatives till you break it down to 0, and then you just write out the answer like we did by multiplying out all the diagonals until you get to 0. When you get to 0, that diagonal is going to be that plus c over there. All right, hopefully this was instructive and helpful for you in making a very complicated but very powerful and useful technique of integration by parts a little bit easier. This one, if you're going to be a math major or engineer, this technique is probably one of the most important to take away with Cal 2. It pops up in Cal 3, differential equations, partial differential equations, all courses that you'll need for an engineering degree.